Hello. So in this section, what we're going to do is actually use the Fourier transform and a bunch of the tools that we've been building up to solve the heat equation and kind of set up the framework to solve essentially any linear PDE that you might want to solve on an infinite domain. Okay. So what we'll talk about, kind of the plan for this video is kind of we'll revisit the heat equation, solve it in one way, and construct kind of these things that we'll call fundamental solutions, after which we're going to go back and take a look at properties of the Fourier transform, in particular, how the Fourier transform behaves with respect to derivatives. And so there we'll solve the heat equation kind of once again in a slightly different way and see that the solutions match up. After which we'll talk about this thing called the convolution theorem, which lets you compute the inverse Fourier transform of a product of functions in a really kind of nice and elegant-ish way. One sort of consequence of the convolution theorem is this thing called Parseval's identity, which is related to, or which shows up in some signal processing kind of areas. So we'll mention this. And then finally, we'll give a brief summary of kind of all of the properties and kind of how we're working with these things. Yeah. Cool. So let's talk about the heat equation again. So here we have the heat equation, right? And this should be, so not quite the heat equation. This should be du dt. Right, so the time derivative of your function is equal to k times the second spatial derivative. And so it turns out that, well, if we take kind of a function of this form, right, or a solution of this form, then it solves the heat equation, okay? And that we can get rather directly just by saying, right, so what is the time derivative of this piece? Well, look through here, the only place that t pops up is this term. And so if you move kind of this derivative in here, just take the derivative, that time derivative there, you're going to pick up a, let's see, minus k omega squared, and then integral from minus infinity up to infinity, c of omega e to the I omega x, e to the minus k omega squared t d omega. Okay, likewise, if you take second spatial derivative, right, where is that going to affect? So this doesn't depend on x, this doesn't depend on x, this depends on x. So if you take two of those spatial derivatives, you're going to get du dx squared of u of x comma t. So two derivatives here, this I omega is going to come down twice. So we're going to pick up a minus omega squared, then integral from infinity up to infinity of c omega e to the I omega x, e to the minus k omega squared t d omega. Okay. So you have a k in front there. So multiply by k there, multiply by k there. And then you see that this is equal to this. So then this representation solves the heat equation. Okay. So that's in general, right? Usually for these problems, we're also given an initial condition. So for this representation to solve or to satisfy the initial condition, right, we'll plug in t equals 0. This piece goes to 1. So whatever these coefficients c of omega are, right, we need to be able to write f of x in this way. And so kind of some ways of saying that, well, f of x is going to be the inverse Fourier transform of these constants c omega. Or kind of going the other way, you could say that c omega, kind of by virtue of some of these Fourier identities, c omega is going to be the Fourier transform of f of x. Okay. Right. So that's where kind of we were at. Okay. And so now the question is, can we modify this integral in some way so that it's a, I don't know, it's in a slightly easier to look at or work with representation. So that's what we're going to be doing. Okay, so we said, so right, u of xt integral of c omega times these two exponentials. So what we're going to do is plug in this expression here for c omega. Okay. And so what we get, we'll just plug it in there. Great. Let's pull out the 1 over 2 pi so we don't have to worry about it yet. And then otherwise we have, right, our initial condition times this exponential coming from the Fourier transform times this other piece that we had in kind of our solution representation. Okay. What we're going to do is we're going to combine, right, e to the I omega minus I omega z and e to the I omega x. So we're going to get that. And then what we're going to do is we're going to change the order of integration. Okay, and so in this case, it's fine because everything's integrable and right, we're integrating over just the entire plane. So we don't really need to worry about kind of a change in the boundary. But we're going to split or switch dz and d omega. Okay, and then this f of z, that can be pulled out, but we're going to be left with this sort of representation. Okay, so all the same pieces are here. We just rearrange them a little bit. And so now what we're working with is, sure, 1 over 2 pi integral of f of z times this expression in here. Okay. And so if we look at this expression, well, we have some function, right? So, right, this looks like a, I mean, it is a Gaussian, right? We have this Gaussian here where that parameter beta is, in this case, k times t. And then we're multiplying by e to the I omega something. Okay, and then we're integrating out omega. Okay. And so this representation looks a whole lot like the inverse Fourier transform, right? Because we're integrating against e to the I omega, right, a parameter, variable. We're integrating, right, this Gaussian right here with respect to omega against this complex exponential. Okay, and in fact, this is the inverse Fourier transform of a Gaussian. You just need to be a little careful about kind of what that function value is. Okay, and so that's what we're going to do. Plug in what the inverse Fourier transform of Gaussian is here, and then see what we end up with. Okay. So recall that, right, so we have an explicit formula for the inverse Fourier transform of a Gaussian. This was, I can write it here. So the Fourier inverse Fourier transform of e to the minus beta omega squared, valued at point x. This was square root of pi over beta times e to the minus x squared over 4 beta. And so what we're doing here is we're saying, okay, well, right, beta in this case is k times t. And then the point that we're evaluating at x, that's this point x minus z. Okay. So this integral in here, right, sure, it looks kind of messy, but we've already computed what this thing is, right? This thing here is exactly this expression here. Okay. So this is what we had on the last slide. Plug in the inverse Fourier transform of a Gaussian into this piece here, and you end up with this representation for your solution u of x comma t. Okay, so sure, it's still an integral, but right now everything's, I mean, assuming our initial condition is real, now everything is real. Okay, and so in a sense, it's in a slightly more comfortable framework for our intuition and functions we're comfortable with. Okay. Cool. So yeah, so this is one way of representing our general solution to the heat equation on an infinite domain. And the nice thing about this representation is, right, one, it highlights the dependence on the initial condition, right? So change your initial condition here. We know exactly how it's going to affect the solution. Well, okay. Change the initial condition. It's going to affect the solution by, right, changing what this integral is, but we can get it in a not bad way. Likewise, right, the other thing to note is that these Gaussians, kind of that, right, we've been mentioning and working with, they play a fairly fundamental role in this representation. Okay, and so one thing to note is that, say 1 over 2 pi times the square root of pi over kt e to the minus x minus z squared over 4 kt, right? The expression involving this and this, the 1 over 2 pi in front, this we can rewrite as 1 over square root of 4 pi kt. Okay, 4 coming from, right, we want this term under the square root, so, right, 2 squared is 4. We have a pi in the denominator, root pi on top, right? These are going to cancel to give you a root pi in the denominator, pi to the 1/2 in the denominator. Otherwise, we pick up this root kt, and then this e to the minus x minus z squared over 4 kt, that's unchanged. Okay. So, right, the thing that doesn't vary in this representation is kind of this piece right here, this Gaussian right here. Okay, we can change the initial condition. This is going to change, but everything else is going to stay the same. Okay, so this piece right here, this Gaussian right here, is kind of fundamental to, right, how we're choosing or how we're able to represent these solutions. And because of that role, we call them, or names for them include influence functions, which is what the book likes to call them. I'm more comfortable calling them heat kernels, just because that's also found extensively in the literature. But anyways, yeah, okay. So this is our first kind of nice representation of solutions to the heat equation. And again, this came from computing the Fourier or inverse Fourier transform of the Gaussian. Okay. Okay, so then we can ask, well, what happens for certain, actual like initial conditions? And so one we might be interested in is kind of this Dirac delta distribution, which we might think of as kind of an impulse, right? And so maybe, right, 0 heat kind of on the real line, and then at time 0 you have this massive influx of heat at, I don't know, x equals 0. And then the question is, how does that massive influx, that impulse of heat, distribute? Okay. So, right, our initial condition is this delta function. And so what we can do is we could say, okay, well, we know how to incorporate initial conditions, plug in delta for f, and then integrate out z, okay? But this Dirac delta is kind of, it's special in that, right, whenever we have an integral of this form and we're integrating out z, and the result of integrating against delta is that you're evaluating the function you're multiplying with in the integrand, you're evaluating that at z equals 0. Okay. So this whole thing right here becomes this function evaluated at z equals 0, which is just e to the minus x squared over 4 kt. Okay, which looks like kind of a standard Gaussian that we're more familiar with. So one way to kind of visualize this might be draw some axes. Okay, so let's take a look. So say x equals 0. If 4kt is small, or if t is small, we're going to get a distribution like that. Okay. Now, as t increases, right, so as time kind of goes on, what we're doing is we're changing these parameters of this Gaussian. And so as t increases, kind of the shape of the Gaussian is going to kind of become more spread out. So maybe this might be t is small. And then let time go on for a bit. We're going to get something like, be like this. So this might be t medium. And then let's see. And then let time go on even more. You're probably going to see something like this. And so this might be t large. Right. And so this is just sketching the profile of heat equation with initial condition and impulse as t increases. Okay, which kind of matches with our intuition, right? We'd expect that heat diffuses away from a source and kind of right spreads out in space. And looking at this, special case where we have an impulse, we know what the solutions look like, and we can sketch these solutions for various t, and kind of see that in these pictures, yeah, it does spread out, right? It does have this diffusive property. Okay. Yeah, and so taking initial condition delta, it's important enough that we call it a fundamental solution. One of the reasons we call it a fundamental solution is that, as we'll see later, kind of if you take the convolution, which is something that we'll define here shortly, of delta with any other function, you just get back your function. And so if you want to solve any other, the heat equation with any other initial condition, essentially what you can do is solve it for this initial condition and then take a convolution of whatever you care about. So we can use this initial condition to solve whatever other initial condition we might want. But we'll talk about that in a bit. Okay. So as an example of this, what we're going to do is we're going to look at a different initial condition. This initial condition is going to be 0 to the left of x equals 0 and 100 to the right of x equals 0. So as an illustration of that, oh, draw my x's again. So this is 100 and 0, and this is a graph of f of x. And in practice, it doesn't really matter what's happening at any individual point, but okay. So using our general representation of solutions, right? The solution to the heat equation takes this form, okay? Plug in the initial condition f of x. This integral, right? We're going to have a 0 when we're integrating from -infinity to 0. Okay? And then from 0 up to infinity, this is going to be 100. So in practice, this integral becomes 100 times, or everything we had before, just 100 in front, and the bounds of integration are now 0 to infinity, right? Again, because these are the bounds where our initial condition is non-zero. Okay. Okay, so what we can do is we can say, okay, well, take this expression. What we'd like to do is, convert it into something that's a little easier to work with and a little easier to interpret. So what we're going to do is we're going to make a change of variables and get this whole thing in here to just be equal to u. Okay. So set u to be, right, x minus z over root 4kt. We end up with an e to the minus u squared in here. So that's that piece. Du, we can compute. In this case, du, right? So the thing that we're kind of integrating with respect to is z. So du is going to be, in this case, minus dz over square root 4kt. Okay. Let me rewrite this. 4kt. Okay. And so then what we're going to do, right, take this, or so move this over to the other side, and I guess move that over to the other side, plug in this expression for dz, which is right here. So this square root 4kt is going to cancel with this square root 4kt out here, and we're just going to be left with a root pi. Otherwise, yeah, we're going to be left with hundreds unchanged, e to the minus that, and then it's just a matter of incorporating the boundary conditions. But yeah, maybe there's a sign, maybe this should be, oh, geez. So to get the signs to work out, you should make this change of coordinates, z minus x, which here doesn't really matter, right? Because we're squaring it, so you can pull that minus out. But then here, that sign is going to go away, and then it'll work out. But yeah, okay. Cool. Yeah, so this is our solution to the heat equation with these initial conditions. So let's make a little more sense of that. So first thing to note, right, what is this integral right here? At least the bounds, you can rewrite the bounds as, right, integral from 0 to infinity plus integral from 0 to x over square root of 4kt. Right, because switch these bounds, you're going to pick up a minus sign here, but then convert this to minus. That minus sign is going to go away. And then what you're doing is you're splitting up this integral between, right, the lower bound to 0 and then 0 to the upper bound. But anyways, okay. So you can use this integral arithmetic or arithmetic of the bounds. This integral we've seen a few times. If you just take the integral from 0 to infinity, you get root pi over 2. Okay. So what we can do is take, so go back here. So take this expression right here, copy it. We can take this expression here and then write this as, right, 100, say, over root pi of integral from 0 to infinity, e to the minus u squared du, plus integral from 0 to x over root 4kt, e to the minus u squared du. Okay. This piece right here is root pi over 2. So root pi is going to cancel with that. We're going to get 100 over 2. That's where we're going to get this 50 from. Otherwise, right, this other piece, not much we can do with here. And we're just going to leave it like that. Okay. Okay, but how can we make sense of kind of this representation? right? So one thing we can do is draw another set of axes. Okay. Right, so the thing here is we're working with these Gaussians. That's a bad one. Close enough. Okay, so what we can do is we can say, great, well, this piece in here, this is the certain integral of a Gaussian, right? This piece right here is computing the area between 0 and x over square root of 4kt. Okay, if x is negative, we're going to be integrating that way. If x is positive, we're going to be integrating that way. Okay, and so we can do is say, okay, well, where are these values? So say this is minus x over square root of 4kt, and then symmetric over there, this is going to be x over square root of 4kt. Okay. And so then let's see. So this thing right here, this you're computing kind of this total area under this curve, right? So what can we reason about this? Well, as t goes to infinity, right? Fix an x, as t goes to infinity, x over square root of 4kt, that's going to go to 0. So what's going to happen is, right, as t goes to infinity, this integral right here, we're going to be kind of getting this area, and then we're going to be computing this area, etc. So this term here is going to go to 0 as t goes to infinity. And so, right, as t goes to infinity, the limiting temperature will just be a constant 50. And this didn't care what value of x we picked. Okay. Which matches with kind of, right, what we saw before, where you let time go on, you're going to converge to an equilibrium solution. Generally, that's going to be constant. Okay. Right, so what else can we reason? So if we go back to this picture, right? So this is the initial temperature distribution. At time 1, you might get something like that. I'll say small time, something like that. Medium time, something like that, etc. Right, but what's happening is heat over here is going to be distributing and flowing over there. Okay, so we're going to get this family of curves that looks something like that, these sigmoidal things. Okay, but what we're seeing in the solution is, right, what is this temperature distribution? Well, take 50, right, halfway, right, kind of half the value at that interface. And then if you're to the right, so if x is positive, you're to the right of that interface, this is just going to be adding to 50, okay, for all time. So you're going to be above kind of the average. If x is negative, then messing with the signs of this, you're going to be taking away from 50. So you're going to be at 50, and then you're going to subtract whatever contribution you're getting here. But anyways, so yeah, so I guess the conclusion then would be this solution, as you vary x, vary t, matches with what we might expect to actually happen for this kind of piecewise constant initial condition. But anyways, okay. Cool. Okay, so all of that relied on, right, taking the inverse Fourier transform, or take the inverse Fourier transform of a Gaussian. And we got that Gaussian because we said, well, here's an expression that solves the heat equation. Let's rearrange things. Oh, look, this inverse Fourier transform of a Gaussian popped out. So what we're going to do now is we're going to kind of go a different direction. Instead, we're going to go back and say, okay, well, we have the heat equation. Let's just take the Fourier transform, see how it plays with derivatives, and then best case, we pick up an ODE, which we can solve, and then we compute the inverse Fourier transform. So that's what we're going to do. But yeah, so to do that, you need to figure out how the Fourier transform plays with derivatives. Yeah, so as I mentioned, right, solve this by explicitly writing out this integral representation. And so now we're going to take the Fourier transform of these PDEs and then see what pops out. Okay, so as I said, here's our PDE, right? PDE we care about. And what we're going to do is we're going to apply the Fourier transform just to everything, essentially. So on the left, we're going to get the Fourier transform of the time derivative. K is a constant, right? You can pull it out of the integral. So on the right, we're going to get a constant times the Fourier transform of the second derivative. Now, throughout, we're always going to be taking the Fourier transform in x, in the spatial variable. We're not going to be taking the Fourier transform in time. Just something to keep in mind. Okay, so let's figure out what these two pieces are. So first one isn't bad, right? Fourier transform, the time derivative is the time derivative of Fourier transform that we can compute explicitly, right? So what is the time derivative of Fourier transform? We're here, and so I'll clarify. So u is a function of both x and t here, and we're just taking the Fourier transform in x. So this is going to be time derivative of 1 over 2 pi integral from minus infinity to infinity, u of x comma t. And so here, again, we're just taking the Fourier transform in x, and then integrate out x. And that's it. Okay. So if we go back and look at this expression, well, this is a constant. Derivative doesn't care. This doesn't depend on t. Okay. The only thing that depends on t is kind of in this bit. So what we're going to do is move this derivative inside the integration to get 1 over 2 pi integral from minus infinity up to infinity of now the time derivative of u, say at x comma t, e to minus I omega x dx. Okay. But the observation here is that, right, this is a function of x and t. Here, right, this is a piece that's important when we're taking the Fourier transform in x. So this whole thing right here is exactly the Fourier transform of the time derivative of u. Okay. So time derivatives don't really care. You can move them in or out the Fourier transform. That's all well and good. You can repeat this to get that the second time derivative, you might say, commutes with the Fourier transform. Okay, cool. So what about the spatial derivative? Here we have a slightly more interesting formula. Okay, and this isn't too hard to get, right? So here, what is a Fourier transform of the x derivative? Well, it's going to be, right, 1 over 2 pi integral from minus infinity up to infinity of du dx. Again, though, u is a function of x and t, but anyways, du dx times e to the minus I omega x dx. So now what we're going to do, this is perfectly set up for integration by parts. So this is going to be 1 over 2 pi times, so So this is going to be our dv. This is going to be our u. So 1 over 2 pi times uv, which in this case is u of x comma t times e to the minus omega x. Evaluated our bounds, which are minus infinity up to infinity. Minus, and so distribute that 1 over 2 pi. One over 2 pi, the integral, infinity up to infinity, of v, which in this case is our u of x comma t, v du. So now we're taking the x derivative of this. Take the x derivative, we're going to have a minus I omega. This term is going to come down. So we're going to end up with a plus I omega u of x comma t, and then just this exponential e to the minus I omega x dx. Okay. And so the observation is that, well, this, say, 1 over 2 pi times this integral, that's exactly the Fourier transform of the function u. So when we take the Fourier transform of the derivative, what do we get? Well, we have I times omega times the Fourier transform of our function. Okay. So in a sense, derivatives become multiplication by I omega. But then in general, right, I mean, u can do whatever, right? So we're just going to pick up this other, I might call like a correction term. So it'd be great if this thing was equal to 0, or it went to 0. Okay, because then we could say that, well, the Fourier transform of a derivative is just I times, or I omega times the Fourier transform. Okay, so what we can do is we can say, well, assume that u of x comma t satisfies, right, as you go out to plus and minus infinity, this function here goes to 0. So if we have this, then this whole thing goes to 0, and we're left with exactly what we wanted, where Fourier transform of derivative is I omega times the Fourier transform. Okay, and so here, this is all just extra notation for kind of Fourier transform. So this is highlighting the fact that we have kind of an operator that we're acting on u by something. Hat is another popular one. The book likes to use capital U and then an overline bar. I'm not a big fan of this, but anyways, point is Fourier transform of derivative becomes I omega times the Fourier transform. Cool. And so if you assume that, right, your function goes to 0 as you go out to plus or minus infinity, as well as enough of its derivatives go to 0 as you go out to plus and minus infinity, which we usually say u, or the function u and all of its derivatives decay sufficiently fast, right? If we have these conditions, then kind of going through the same process, right? Integration by parts, keeping track of the boundary pieces, what you end up getting is that the Fourier transform of the nth derivative in x is going to be I omega to the n times the Fourier transform. Okay, so again, right, if your function behaves like this, then Fourier transform of a derivative is just I omega times the Fourier transform. Okay, which is super nice for solving PDEs, right? Because if we have a PDE, apply the Fourier transform to both sides, anytime we have an x derivative, that's just going to turn into kind of a multiplication by a polynomial times this Fourier transform. And so then in practice, what we could do is factor out that Fourier transform, and we just have, right, time derivative of the Fourier transform is equal to something times the Fourier transform. That we can integrate, that we can solve for a rather straightforward way. Okay, so what are we going to do with these these facts. So, right, here's the PDE we care about. And we're just going to assume that our solution tends to 0 sufficiently fast. Okay, so we don't have to worry about the boundary, those correction terms. So apply the Fourier transform to both sides. What happens? Well, here, this and this, these commute. So this just becomes time derivative of the Fourier transform. On the other side, we have Fourier transform the second derivative. This we're going to pick up in I omega squared times the Fourier transform. Okay. Yeah, so right, what we can do is, so what I'm going to do is I'm going to write this as, right, ddt of u hat, or the Fourier transform of u. This is k, I squared is -1, so minus that. Omega squared is omega squared, so minus k omega squared u hat, right? This is an ODE for the unknown function u hat. So what we can do is we can say, right, say du hat, so move this dt over there, move this u hat down there. We're going to get du hat over u hat is equal to minus k omega squared dt, right? The standard way for solving this kind of stuff. So then ln of u hat is minus k omega squared t plus some constant, so that u hat, and again, this is a function of omega now and t, is going to be some constant times e to the minus k omega squared t. Okay. Right, and this is a main utility of using the Fourier transform. Derivatives turn into polynomial multiplication, which plays very nicely with kind of the general form of these things. We can integrate fairly nicely. Okay, right, so this ODE right here, we saw it has a solution like that. And so the thing to keep in mind is, right, when we solve this ODE, we were treating this ODE as just in kind of time, right? Time was our one variable. And so we were keeping omega constant. So in general, though, right, whatever ODE that we solve here, it depends on omega. So certainly, yeah, depends on omega here, but the constant that we get from kind of this integration, this constant depends on omega as well, right? Change omega, you're going to get a different ODE, possibly different constant. So this constant here should also depend on omega. So what we're going to do is we're going to say, well, yeah, let it depend on omega. So we're going to say, right, the Fourier transform, the solution that we're looking for is going to be some function of omega times kind of this other piece that we picked up. Okay. Great. So the solution to our heat equation is, we don't yet know what it is, but we know what its Fourier transform is. Okay. So the next step is we'll take the inverse Fourier transform, right? Kind of apply this F inverse to all of this. F inverse and F cancels, so we're just left with our function u. So u of x comma t, inverse Fourier transform of the Fourier transform, what we wanted. This, right, we have an explicit form for. So plug this in, we get this thing, okay? And so now apply this inverse Fourier transform, and we get an expression like this. Okay, but notice this is exactly the expression that we started with, right, way back when. Okay. We can scroll back. Maybe I shouldn't scroll back. Right. C of omega e to the I omega x e to the minus k omega squared t. Right. This is what we start with, showed that it solved that. Okay. But what we can do is, starting from just properties of the Fourier transform and derivatives, we end up with that, oh yeah, right, we can get a different way, which is comforting, right? The kind of system is, what's the word? Consistent with the same representation. Cool. Let's see. Yeah, so the observation here is that, right, when we took this inverse Fourier transform, in a sense, we were taking the inverse Fourier transform of two functions, right? The product of two functions. Okay. And so what we'd like to do is say in general, well, what is the inverse Fourier transform of product of two functions? And we'll see that this shows up enough that it's worth kind of talking about. And it goes by the name of what we'll call the convolution theorem. Think of it as a technique to use. Right, so kind of in the last bit, right, what we did is we solved this, sure, by applying the inverse Fourier transform, but the observation is that these two functions that we were working with, they themselves are Fourier transforms of something else, right? The C omega in practice is going to be the Fourier transform of the initial condition F, little f. And this piece right here is a Gaussian. Okay, and we know how kind of Gaussians Fourier transform, right? So in this case, e to the minus k omega squared t, that turns out to be the Fourier transform of this Gaussian right here. Yeah, okay. Which you can get by, right, I mean, if you want to verify, take the inverse Fourier transform of this, inverse Fourier transform of this. So this inverse Fourier transform, you end up with just this, but over here you have the inverse Fourier transform of this, which we explicitly computed. Okay. So, and another way to say this, right? So this is a function of omega. We're going to call it h. Right? And so what we have is our function h of omega is the product of two Fourier transforms. And we want to compute the inverse Fourier transform of capital H. Okay. And one important fact is, or one important thing that we'll be using is the fact that both of these are already Fourier transforms of some functions. Cool. So, right, written explicitly, if we have this product of Fourier transforms and we want to take the inverse Fourier transform, right, we're going to call that function little h of x, inverse Fourier transform of capital H. This is by definition what that inverse transform is. So our question is, can this take a slightly nicer form? Okay. So to fix notation, this capital F of omega, right, Fourier transform of little f, capital G of omega, Fourier transform of little g. Okay, so what we're going to do is we're going to say, well, hey, we know what this is. It's product. So plug the product in, move things around, see what we get. Let's do that. So this is all from the last slide, right? This is the function that we care about, which is the inverse Fourier transform of h, which by definition looks like this. So plug in what h is. Well, it's a product of two Fourier transforms. Okay. So now what we're going to do is we're going to explicitly plug in kind of the integral representation for, say, g. Okay. You can do the same thing by plugging in for f. You're going to get similar sort of result, but now we're going to focus on g. Okay. So that's what this next line is. So this thing right here, this is exactly this piece right here, right? We're just plugging in the definition of the Fourier transform for G. Okay. F is unaffected. This is unaffected. Okay. But now what we're going to do is we're going to move things around. Okay, so this e to the I omega x, that we're going to bring in here. We're going to change the order of integration because we have, right, we're just integrating over the whole plane, so that's no issue. G of z, we're going to pull out. The 1 over 2 pi, we're going to pull out. And this f of omega, we're going to move in. Okay, so we need a second, just maybe write them out single step by step, but we're shuffling things around so that in the end, what we end up with is this f of omega come in here, d omega come in here, this come in here. Combine e to the I omega x with e to the minus I omega z. We're going to end up with e to the I omega x minus z. Otherwise, we have the integral of f omega times e to the I omega x minus z, d omega. And this looks an awful lot like an inverse Fourier transform. Right? What we're doing is we're saying, well, here's this function f, take the inverse Fourier transform and evaluate it at x minus z. Okay. The assumption was that this was the Fourier transform of little f. So if we plug that in, that's exactly that. Okay. So 1 over 2 pi is unaffected, g of z is unaffected. But this whole thing, because of how we defined f, is equal to little f, but now evaluated at x minus z. Okay. And so this was our h of x. Okay. So what we've done is we said, sure, what is the inverse Fourier transform of this product? Well, now it's this interesting integral involving kind of the two functions that were Fourier transformed to get that product. Okay. Right, so this integral right here shows up enough, it's important enough that it has a name. This, well, in particular, this thing right here, this we call the convolution of g and f. Okay. And so what we could do is we could kind of, right, go back in this derivation. Instead of plugging in for g, we could plug in for f. Okay. And then you're going to pick up, yeah, and let's see. Yeah, if you plug in for f here, you're going to get an f of z, f of z, f of z, and then otherwise this is going to be a g of x minus z. So, right, switch the roles of f and omega. You can get this from the derivation. You can also do a change of coordinates. Say u is equal to x minus z. And so then z is equal to x minus u. Right, and then that's going to switch the roles of those two. But anyways, yeah, so this integral right here we call the convolution. Other notation is f star g. Okay, so you see this expression, you say, ah, that's the convolution. Where are we evaluating it? We're evaluating at x. Great. Take one of the functions, plug in what we're integrating over, take the other function, take where we're evaluating minus what we're integrating over, and that's this convolution. Okay. All over the place in signal processing and a lot of other areas, but for us, it's going to kind of help us solve the heat equation and other PDEs in certain contexts. Cool. Yeah, so another way to write kind of this result is, right, well, again, if capital H is a product of these two Fourier transforms, then the inverse Fourier transform of H is a convolution, well, 1 over 2 pi times a convolution of the two functions. Okay. So what does this look like with the heat equation again? Right, so what we found was, right, the Fourier transform of the solution was the c omega times e to the minus k omega squared t. Right, this is the Fourier transform of the initial condition f. This is the Fourier transform of the Gaussian kind of written right here, right? And so as written, right, well, take the inverse Fourier transform of h, that's going to be little h, which here is a function of x and t, but all of these Fourier transforms are just in x, not in t. So this theorem, this convolution theorem, or this identity right here, tells us that, well, h is going to be 1/2 pi times a convolution of, right, what we got for this. So let me actually draw that. So this piece shows up there. Convolution of, right, the function that we kind of took the Fourier transform to get c, and then the function that we took the Fourier transform to get this Gaussian e to the minus k omega squared t. Right, so it's 1/2 pi convolution of these two functions, evaluated at x. And so then, okay, well, what is this definition? Well, integrate out kind of this dummy variable x, and then say this one in here, you plug in x minus z. And so that's exactly what we have here. Right, so a third way that we're getting the same sort of, representation of solutions to the heat equation. Just now we're explicitly, or kind of we're using this convolution theorem to quickly go through evaluating what the inverse transform of this thing is. But, cool. Okay. Yeah, so kind of everything in the last few slides, right? This is kind of our general procedure for solving heat equations or similar linear PDEs on infinite intervals, right? Take the Fourier transform in x, okay? We know how that plays with derivatives in t and x, okay? Take the Fourier transform. That's going to give you an ODE in t. Solve that ODE. Okay. Apply the initial condition to figure out what the C omega is, which the book writes this out explicitly, but this really kind of ties in here where, sure, your C omega is a Fourier transform of the initial condition. How do we get the kind of actual solution? Well, apply this convolution theorem to say, well, here's the inverse Fourier transform of kind of the product that we'll get in the ODE. And then you get the solution that you care about. Okay. But the strategy in general is take the Fourier transform of the PDE, solve the ODE in time, take the inverse Fourier transform. Okay. Cool. So kind of this convolution theorem gives this nice little identity that, as I mentioned, shows up in certain kind of signal processing or related areas. So we'll talk about that this kind of briefly. Okay, so right, we saw, well, take the inverse Fourier transform of a product. Okay. Right, so this thing right here, this is 1/2 pi, the convolution of f and g, say evaluated at point x. Okay, so if we explicitly write out this integral, that's going to give this. Otherwise, if we explicitly write out this integral, right, this is the inverse Fourier transform of the product. So this identity tells us that, right, these two integrals are the same. This holds for all x, okay? So if we plug in x equals 0, right, this goes to 1, that's 0. So we're left with this identity, okay? Okay, great. So now what we're going to do is we're essentially going to plug in, instead of f here, we're going to plug in almost G. Okay. So what we'd like to say is that this is going to give us some sort of measure of like the total energy in the signal or the function or the sample G. And then this is going to tell us something about the total energy kind of in the wave numbers and the frequencies and kind of their amplitudes that we're picking up. Okay. So how can we make that a little more quantitative? Right, so this integral identity, right, doesn't matter what f and g, right, any functions work, okay? So what we're gonna do is we're gonna kind of choose f so that f of negative x is equal to kind of the complex conjugate of g. And so this is just notation that we're using g star, that's the complex conjugate of g in this derivation. Okay, so question is, right, how do the Fourier transforms of f, where we choose f to be this, and the Fourier transform of just g, how do those Fourier transforms relate? Okay, well, let's just take the Fourier transform of f, that's this thing right here. Change coordinates so that kind of you're going from x to minus x. Right, so then dx is going to become minus dx, but the bounds and the integrals are going to flip so that kind of the flip these back, it's going to cancel with the minus from that, but in any case, so this thing is equal to this thing. Okay, now we're choosing f so that f of minus x is the complex conjugate of g. So plug in for that, we get g star, the complex conjugate of g. Now what we can do is kind of, in a sense, like factor out the complex conjugate. And so that's kind of this other notation that we're a little more used to. So the complex conjugate of this product, well, yeah, if you take the complex conjugate of this product, it's going to distribute complex conjugate of g, complex conjugate of this Gaussian, or not Gaussian, this exponential, complex conjugate of this exponential. The minus just becomes a plus, so we end up with that. We're all good. But if you take this complex conjugate and like factor it out, kind of, so it's outside this integral, then what we end up with is a complex conjugate of the Fourier transform of g. Okay. So if we choose f in this way, then this capital F of omega is going to be the complex conjugate of g omega. Okay, cool. So let's plug it into the identity, right? This was the identity. Plug in f of minus x is g, or the complex conjugate of g to here. Likewise, we saw that for this choice of f of omega is g star of omega, complex conjugate of g. So we end up with this expression, which is all well and good. But we recognize that, right, this is some complex number, possibly complex number, might be real, might be complex. But what we're doing is we're multiplying this number by its complex conjugate, right? So in general, right, z, so if z is equal to a plus ib, right, z times its complex conjugate, a plus ib, a minus ib, distribute it, you're going to end up with a squared plus b squared, which kind of is this vector norm, right? Treating this complex number as a vector in two dimensions, vector norm squared. But anyways, yeah, so because we have g and its complex conjugate, and then capital G and its complex conjugate, what we end up with is on the left, we get this integral where we're integrating over the kind of absolute value or the norm of g squared over the entire kind of domain for the signal. So on the left-hand side, on the right-hand side, we're integrating the norm of kind of the Fourier transform, or kind of the frequency with amplitude of the signal. Right, so if you kind of interpret in that way, then one way to kind of make sense of these is over here, this is the total energy kind of in space for your signal. Whereas on the right, this is going to be the total energy kind of per wave number or frequency, again, for your signal. And so, especially if you normalize your signal so that this integral becomes 1, okay, what we end up getting is kind of on the right-hand side, this object right here, we can interpret it as some probability distribution for where we might find frequencies, okay? And so, yeah, this is often called this spectral energy density, okay? And so, of course, right, normalize the signal so that kind of this total energy is 1. This total integral is going to be 1. This thing is positive. So yeah, we interpret this as a probability distribution because it, right, total probability of anything is 1. Yeah, okay, anyways. So even without kind of this interpretation and getting closer to signal processing, this identity is still, I don't know, it's a nice identity. It gives us other nice identities. Cool. Okay. So the last bit I want to mention is just kind of summarizing a bunch of the things that we saw here. Right. So the one thing to also keep in mind is that kind of the sign conventions that we're using are flipped from the book. But right, so here, interpret this as your function. This, you're taking the inverse Fourier transform, you end up with little f. Otherwise, if you're given little f, this is the Fourier transform, you get capital F. Okay. And so the kind of main pieces that we've been working with are, well, if you have a Gaussian, we know how to Fourier transform that. We're going to get something like that. If we have a Gaussian in frequency space, we know how to take the inverse Fourier transform, and we get another Gaussian. Great. Time derivatives, when we take the Fourier transform in space, time derivatives don't, they just commute with the Fourier transform. Otherwise, if we have space derivatives, then the Fourier transform converts them to multiplication by I omega, or multiplication by I omega squared. This is all assuming that kind of the function that you're Fourier transforming goes to 0 fast enough at plus and minus infinity, but we're usually happy to make that assumption. Cool, so this all was new here. The final new thing is this convolution theorem, right, where the inverse Fourier transform of a product of Fourier transforms, that becomes this convolution of kind of the two functions that were Fourier transformed. Okay, so these pieces right here are going to be the main, I might say, like building blocks for solving PDEs with the Fourier transform, right? Take the Fourier transform, solve the ODE. You're going to get it generally, you're going to get it as a product of something depending on your initial condition and some sort of Gaussian. Take the inverse Fourier transform, you can write that out explicitly as this integral. Okay, this is kind of the technique that we have, and how we'll be solving these PDEs using this Fourier transform. And I think that's it for this chapter.